Welcome back to ECE 220. We're half here in screen and in attendance. We'll see if we can get the other one working, but maybe the projector is not going to cooperate. I guess I need to call that in. I didn't notice that until now, but at least you can see one screen. Is that true? Please remind me if you lose that one, and we'll go to a whiteboard, I guess. We won't have any kind of projection. Talking about what you need to be doing, now we're going into Chapter 8. We only have one more chapter after 8, and then we're finished with this course's content. We're going in and through Chapter 9. We are covering Chapters 1 through 9. The final is comprehensive. And we are going to start Chapter 8 this week. It may not be tomorrow, but it should be Wednesday, I think, is what I'm guessing. Homework 9, which is due on Tuesday, is the last material for exam number 3. So you will be tested over that material on exam number 3. And we will have a review for exam number 3 a week from today. Prior to that, Lab B, or Group B, Section L, will be having their lab number 3 on Tuesday. Group A, your lab number 3 report. If you're in Group A, which is the majority, it's due Wednesday. And we will not have class this Friday or next Friday. So you can tell your friends, if you're afraid they're going to show up on a Friday, you can let them know. Otherwise, they will show up for the one time and be greeted with no class. This is throwing me off, having one screen. I'm used to seeing both. Exam number 3 is a week from Thursday, and that will cover chapters 5 and 6, which includes homeworks 7, 8, and 9, and it might be a plus again. I have to figure out if we'll have some phasor topics or some complex analysis on exam number 3. Today what we want to do is go through an example, and there's going to be many switches. And the switches will throw us into new configurations of our circuit, which means that now we have to worry about different things happening under those conditions. And it's helpful if we're going to think about Fifey. Is Fifey? Here, Fifey. Here, boy. It sounds like a dog. But anyway, we have Fifey for final, initial, final, and exponential. And if we obey that structure, we can do that because we have natural and step response characteristics. That's all we're talking about in this chapter. And those rely on knowing what the time constant is to give us the exponential. So we need to find an effective resistance. We need to know initial conditions. And we need to be able to find final values. And once we have that collection of information, we can apply Fifey and obtain our answer over certain intervals of time. Here's the example. And I'll give you 2 seconds to digest it. In fact, there's only one inductor in that circuit. And all the other things are switches, constant supplies, and resistors. And these switches are turning off and on at different times. We have one switch that opens at time 0. The middle switch opens at time 2, and the rightmost switch actually closes at time 2. So we have 2 switches that are at the same time. They're just going in opposite directions. But we want to now find the inductor current, I sub L of t, for all time. And I didn't label the values of the resistors, but they're in units of ohms. That's what the ohms in parentheses means in the upper right-hand corner. I did label the inductance units, that's millihenries, and the sources are in volts. And hopefully you've now had a chance to sort of quickly sketch or reflect on that circuit and what that means relative to finding what's happening to our inductor current. And if we want, well, maybe I should have said T for all time, because we really want to find what's that inductor current initially. What is it prior to or at time 0? And for that, we really need to find what does this circuit look like for t less than 0. What happens initially in this circuit? Can you now sketch the circuit for the time interval from minus infinity up to time 0? Two of the switches are closed. The rightmost switch is open. That means we can neglect that resistor in series with the 90 volt source. That's not connected yet. But the other pieces of our circuit are in play. So if we sketch this now for t less than 0, we should end up with the following. And what else do we know is true if this circuit has been like this configuration for a long time, for an infinite amount of time, from minus infinity up to t equal to 0? We have a constant source. Can we now modify this circuit? We've now accounted for the locations of the switches. Can we say anything more now about this circuit? Or can we simplify it any? Can we do anything more with this circuit? And now we have it being driven by a constant value. And what's an inductor do when it has DC or constant sources applied to it? Does one of two things, right? We have an inductor and a capacitor, and they do different things. They're duals of each other. If you now put a battery, apply a battery source to an inductor, how does it behave? It shorts. So in fact, we can simplify this circuit. We can get rid of that, and that inductor now becomes a short. And this is still our inductor current, I sub L. Now that we're in a review period, now we simply need to find I sub L in this resistive circuit with a constant source. And what do you want to apply to find I sub L of 0 minus? What kind of an analysis? Now you're trying to do some analysis. What kind of analysis do you want to perform? Chapter 4. Mesh current analysis, node voltage. Somebody just said mesh. How many mesh currents do we have? Now we have 3 panes there, and pane might be the key word here. That might not be the best, right? That might be a pain, using a different spelling of the word, but how many essential nodes do we have? If we call this our common, and we look at that as a node, now does it look a little bit less involved? I mean, we have a lot of currents to keep track of, but now we only have the one unknown voltage, V sub 1. And if we can find V sub 1, we can find I sub L. The analysis we're doing is node voltage analysis. It only involves one node voltage. We can write a KCL at that top node. KCL now, we have this current, that current, this current, and I sub L. And those all are leaving the node, and they should sum to 0. The one going to the left, the only current going to the left, in terms of V sub 1, that's V1 minus 60. It's where we are, minus where we're going, divided by 4. All the others just have V1. We have V1 over 12, V1 over 6, and V1 over 3. That might look a little messy, but we can clean it up a lot if we just multiply all sides by 12. Then we get rid of those fractions. Or now we have 3V1 minus 3 times 60 plus V1 plus 2V1 plus 4V1 is equal to 0. We add up all of our V1s, and I think I see 10 of those. We have 10 V1, and put the constant term on the other side, which is 180, or now V1 is 18 volts. And now we can solve for I sub L, which is really I sub L for all time less than 0. But we're just interested in what it's doing at 0, which is I sub L at 0 minus, just to the left of 0. That's now V1 over 3. We now know we're starting. Our initial current going through that inductor is 6 amps. Okay, we've gone an infinitesimal distance in our solution. We wanted I sub L for t greater than or equal to 0. We've now found it at 0. We have it on the minus side and the plus side. Why? Why do we know I sub L on either side of 0. What do we know about an inductor? Eli. Okay. If we know Eli, what does Eli tell us? It's continuous, doesn't it? Now we know that because of di dt, the current is continuous. We know now I sub L at 0 minus. We know I sub L at 0 plus. V is another story. What the voltage is doing. So now on the exam, if I ask you for V sub L of 0 plus, that might in fact be something different from V sub L of 0 minus. Okay, but now we are interested in moving beyond 0. What's the circuit look like now for time bigger than 0, but now we have something switching at 2, so let's only go as far as 2. What's the circuit look like between 0 and 2? Now we really just disengage the leftmost switch. So we throw away what's on the left and keep what's on the right, except for the far right. The far right is still not engaged, and we really just have the middle portion of our circuit. Or now we have, for t between 0 and 2, we have this. Here's 18, here's L. L is still 150 millihenries. This is 3, and this is 6. And this is our circuit for time t between 0 and 2. Now what? Now what do we do? Is there anything we can do? We want to go beyond 0. We want to get t from 0 all the way up to infinity. And right now we're focused on this time interval between 0 and 2. What do we know? Well, we know what I sub L is starting at. We know I sub L of 0 minus. And because the inductor current is a state variable, which means that current is continuous, I sub L of 0 minus is I sub L of 0 plus, which is 6 amps. Does that help us? This is what the circuit looks like. We now know where we're starting. We're starting with a current flowing through that inductor of 6 amps, but now that inductor is engaged. It's not reached, it's not in a steady state configuration. We want to go there if we can. We want to start our way towards 2, and how do we analyze this circuit? Do you want to go to the math building? No? Okay, let's stay here then. but we're still going to have to use some tools, right? We've already solved this circuit. This is an RL circuit. We have more than one R, but can we find an effective resistance? Does that inductor just really see one resistor attached to it? That inductor is by itself in terms of energy storage, but now it's surrounded by resistors, but in reality it just kind of feels like there's one resistor next to it. How do we find the effective resistance that that inductor sees? What is R effective? How do we find the effective resistance that that inductor feels or senses or sees? How do we find the effective resistance for an inductor or a capacitor? We kind of step out of the circuit and say, okay, I'm stepping away and I'm going to leave terminals A and B where I was, and now I need to find what I see at terminals A and B. What's the resistance between terminals A and B? Let's now redraw the circuit and say, okay, here's where I was. Now I'm talking as if I'm the inductor. Have you guys ever pretended to be somebody you aren't? Now we're pretending to be an inductor. I am. You don't have to be, I guess. Maybe you'll be a capacitor tomorrow or something. I don't know. You hold a lot of charge. It's a Monday. I apologize. Okay, there we are. Does that help? All right, now we'll give you a quiz. R sub AB, what's the resistance between nodes A and B? What's seen between A and B? Is it 27? Is it 9 in parallel with 18? Is it 27 over 3? Or is it the parallel combination of 9 with 18 tripled? And when we get that 3 in there, that's kind of making us think, oh, we must have a delta, a y. All right, now I do need your answer. You ready? You know the drill. When I count to 3, you show me either 1, 2, 3, or 4 fingers on one hand. I'm not telling you for 6 possibilities. Now I just have 4, not even 5. 1, 2, 3. Good. All right, so we are seeing that that's now 9 in parallel with 18, which in fact, if you do the math, it better be less than 9. It's now 6. So now we have an effective resistance of 6. That's our answer. If we have R effective, which we were calling R sub AB, is now 6. Now what do we do? What was our circuit? Now we have a circuit that looks like that. And that circuit is going to give us what kind of response structure? What have we talked about in Chapter 7? RL and RC responses. We said natural response and step response. Is this now a natural response structure or a step response structure? Is there a source or is there not a source present? No source. This is naturally how that circuit wants to behave. So this is now a natural response. And the only response now is this magnetic field has been energized to the tune of a current of 6 amps in that going through that inductor. Now that resistor is going to dissipate the energy in that circuit. And what's our structure going to look like for I sub L of t? Do you know where we're starting? We found I sub L of 0 minus. We still haven't gotten past 0, have we? But we now hopefully have a feel for how this is going to move beyond time 0. We started at 6. What's the structure of I sub L of t? Is it a sinusoid? Is it a constant? Is it something I haven't yet said? It's an exponential, isn't it? So this is now I sub L of 0 plus e to the minus t over tau. And we don't know yet if we are going to be finished with this exponential decay by the time we reach 2, or if we'll still be partway to our final destination when we reach 2. We need to figure out what's our time constant. How quickly are we decaying? We need tau. What is tau? Is it RL? And what's R? Was it 6? We've got a lot of 6s floating around, don't we? This would be 6 times 150 milli. This would be 150 milli over 6. And this would be 6 over 150 milli. Which of those is it? Your fingers are getting some workout today. 1, 2, or 3? So is it one of those 3 possibilities? 1, 2, 3. All right, we've kind of forgotten the time constant. RC is for capacitors. L over R is for inductors, for time constants. Right? So you'll need to know that by, wow, exam 4, is that right? Is that where we're at here? Exam 3 is a week from, no, yes. Exam 3 is a week from Thursday. Wow. Should be this, which is how many quarters are in a $1.50? 6. So this is now 25 milliseconds. We have a time constant of 25 milliseconds. The others, you could do dimensional analysis to check and say which of these combinations of R and L, if you've forgotten, give you seconds. And if you start doing R and L multiplied together, you're going to get something messy. The same with R over L, you're going to get 1 over seconds. That's not so messy. But L over R, you're going to get seconds. So the units will be consistent if you've forgotten which one is which. Or you could sort of rederive the differential equation and convince yourself that T over tau, tau needs to be L over R. All right, another, and now I'm even exercising more of your hand. Here, we have 25 milliseconds for our time constant. What is the approximate value of that inductor current by the time we get to 2? Is it e to the minus 1 times 6? 6 being the initial value of our current. We're starting at time 0 with a current of 6. We're now exponentially decaying from that, and we have a time constant of 25 milliseconds. It's 1, 2, 3, 4, or 5. Each of those integers are the exponent on 0.37, or e to the minus 1. Which one is it closer to? 1 through 5. Ready? One, 2, 3. Should be closer to 5. It's beyond, it's less than e to the 5, e to the minus 5. It's less than that. We're more than, what's 5 time constants? 5 times 25 is 125 milliseconds. That's 0.125. We are now we're quite a bit less than this. This would be 1%, less than 1%. We are less than that. So we now are saying that I sub L of 2, well, is going to 0. So we're going to be within that 5 time constant window of time from 0 to 2. What's this look like? What does I sub L of t look like so far? Maybe I should have done this in hundreds of milliseconds. This is going to be hard to sketch very accurately. We started at 6. And now within 125 milliseconds, we're already down to 1% of 6. So in less than, or in a little bit more than, what, a tenth of a second, that's why I said I didn't draw this or didn't give myself much room for sketching. Do you see that we're now quite quickly to a steady state value on a time scale of seconds? So it's hard to even see. What's the circuit look like? So now, what? We were here, and then we quickly fell off the cliff, where that exponent was now with a time constant of 25 milliseconds. So within 125 milliseconds, we're basically gone in terms of the current flowing through that inductor. We wanted to know, what's the current look like for all time? Now we have this sharp transition to 0. What happens beyond 2? What is the circuit for time t bigger than 2? Now we get to go over and include that rightmost piece. At t equal to 2, the middle switch opens and the right switch closes. So we're now basically at a steady state from close, a little less, well, let's say at 0.2 seconds up to 2, we're at 0. And now at 2, we see something new for our current. We see a new circuit. And what's that circuit look like now? Well, now we just draw that 150 millihenries and 18 resistor in parallel with a series resistor and a source. So let's now sketch that. Here's what we have. We now have the resistor and inductor in parallel. Now what? What do we know? We know I sub L of 2 is, for all intents and purposes, 0, correct? Because it was 0 all even by 0.2. So a factor of 10 beyond that, we're definitely exponentially, we're gone. We now have no current flowing in the inductor initially. Can we find what happens? We're interested in this. And we know right when that switch closes, we see this configuration. But then after we've sat there for a while, now we have this circuit will be in steady state. So now we're looking at another infinity time frame. Can we find I sub L at infinity for t greater than 2? Can you now redraw this sketch after we've been beyond 2 for a long time? What's the inductor look like to constant sources? It shorts. Can you now re-sketch this circuit for time closing or approaching infinity, which isn't very far beyond 2, since we didn't go very far beyond 0 before we reached a steady state with our current. If we now look at as t goes to infinity, this is now what we have. And what's I sub L at infinity? This is Ohm's law. Can't get any more straightforward than this. So now this is 90 divided by R, or 4 amps. When do we get to 4? Or what's I sub L of t now look like? Now we know that we started at 6. We fell off a cliff. And then we went to 2 at 0. And then at some point, we get back to 4. When? When do we get back up to 4? Is it clear, the thinking process, or what's going on? we had a circuit and we threw some switches. The first set of switches that were thrown said, oh, we were at 6, now we exponentially decay. And we know what the exponential rate was. It was governed by 25 milliseconds. Now what do we do? Now we want to know, how do we get to 4? And how do we get there? Do we do this? Do we do this? Do we do this? How do we get from point A to point B? We're trying to get from 2, time 2, up to 4, and we want to know how long do we get there. How are we going to answer that question? What do we need to know? When or at what time do we get to 4? And how do we get there? Do you have a clue? Whoa, no more help. Okay, show me some fingers. No. What are we dealing with now? If we go back to this circuit, this is what our circuit is for t bigger than 2. Does that help us? Can we get a sense from this circuit how we're going to approach 4? And I left you without the correct approach. Better be exponential, right? We have an RL circuit, and it's building back up its current exponentially. It's going to have that shape. We just need to know, when do we actually get up to 4? To give us a clue, let's go back to our circuit. I needed to mix it up a little bit. So now we have a battery over there instead of a circle, but it's still an independent voltage source. This was 45 over 2, this was 18, and this was our L. What do we do with this? What are you thinking? Are you finished thinking for this morning? How do we approach this problem? Is it similar to what we had, or what kind of a response are we looking for? Natural or step? Step, we have a constant input. Can we actually find an effective resistance that inductor sees? How did you find equivalent resistors in the past when you were finding Thevenin equivalents? Let's now remove that L. And what do we do with a voltage source? Open it or short it? We short it, and now this is our new R effective. This is 18, 45 over 2. And those two are actually in parallel. So now the new effective resistance for this time interval beyond 2 is now 18 in parallel with 45 over 2. And that was selected. 45 over 2 is 22.5. We need to be less than 18. It actually ends up being 10 ohms. What's now this time constant. What's the formula? We have an RL circuit. This is now L over R. The L is still the same. The R is this R effective 2, which is 10. Now we have an even shorter time constant. Now it's 15 milliseconds. It's only going to take us 5 of those, or 75 milliseconds, not 125, to get to 4. So that now, if we look at this, you can do a better job of drawing an exponential, but that now has a, you can see it, it's just clear. This now has a time constant of 15 milliseconds. So 5 tau, which is the interval, the 1% time interval, is 75 milliseconds. 75 milliseconds beyond 2, we are up to 4 amps. And before that, we were at 6. We dropped down, not as quickly. That was a time constant of 25 milliseconds. And that's now what I sub L of t looks like. We were at 6, we switched, and pretty quickly fell off, went to 0. Then we switched again, and we very quickly went back up, not quite as far. We went up to 4 amps. Can we push this any further? What's another set of questions? That could be asked on an exam. What if I now, instead of currents, I said, well, what's the voltage of the inductor at 2? And does it matter if it's plus or minus? What do we know about the inductor relative to the current what do we know about the voltage of an inductor versus the current of an inductor? This could be different. 2 minus and 2 plus. What's the inductor's current at 2 minus? What's the inductor's voltage at 2 minus? 0. So this one was 0. Why was it 0? It was a short, wasn't it? And we had no current flowing. What's V sub L at 2 plus? What's going on here? What's the circuit? Now we have this. And what do we know is true right at 2 plus? What do we know about I sub L? What do we know is happening there? We know KCL is always true, correct? We have no current flowing in the left branch. All the current is going to be flowing in that rightmost mesh. Now you can figure out what the voltage is across that inductor. It's going to be the same voltage as what's across that 18 ohm resistor. And what's the voltage dropped across that 18 ohm resistor? At 2 plus. Isn't that a voltage divider? Now you could find V sub L of 2 plus. We know V sub L of 2 minus was 0, but now V sub L of 2 plus is instantly something other than 0. It's not continuous. It's jumped up to 18 over the sum of those resistances times 90. And I think that ends up being 40 volts. So it instantly spikes to 40 volts, and then it will decay exponentially. Questions that could be asked and answered on the exam. We'll pick up with more switches tomorrow.